After the class someone was asking about this doubt, right? How these two probabilities are what? Equal, right? So you are actually getting that random variable based on that observation of what? The experiment. The outcome of the experiment, it is mapped to that real line, is what we call it as random variable, right? You have multiple choice to map it, isn't it? You can choose experiment which is mapped to that random variable y, the same outcome, right? I can map it to the random to y and x are what? Different, and then we have a relationship between these two random variables. In that case, we have to look which that two random variables are actually equivalent. And this probability associated with these two random variables are going to be what? Equal. So that's what you are getting from this. So this is equal to what? Probability of x ranging from what? Minus root y to plus root y, right? So this is fx of root y minus fx of minus root y. This is the way how it is getting related. And of course, for getting what? The density function, you can differentiate on both sides with respect to y, because this is what? Function of y here, right? This is fy of y. So I can comfortably take what? The differentiation on both sides to know about this density function. Is it clear? So this is the way how the transformation of random variable is coming, right? And remember that one more point is, yesterday when we are discussing about this 2D conversion, I told a small rectangular portion in that xy is converted to what? The parallelogram in y1, y2 plane. But it is not necessary that it should end up with what? Single parallelogram. Right? So I told you have a straight line, it is mapped to what? The curve in y1, y2 plane. It need not be the single curve. Right? You understood what I am telling? So yesterday whatever we are discussing, that x1, x2 plane, I have drawn the straight line, vertical bar, by keeping this x1 as what? Fixed. And I try to find out what are the possible, set of values of what? y1, y2 in this y1, y2 plane, right? And I have simply drawn as what? Some arbitrary curve, right? You remember that? But it is not necessary that, the single straight line, because of the function what we had it, right? It need not be converted to what? Single curve. You can have multiple curve in this. It means that we have to look for the multiple parallelogram associated with that area, right? So for example, if I choose another 1D plot, something like this, the density function can be like this also, right? So in that case, if I am choosing some value y here, your x region, right, it is not going to be the single region like what we had it here, isn't it? So whatever is lesser than this, you have this multiple region, isn't it? Some portions is above it, right, and this region is above that, isn't it? So I'm talking about this case, the probability of y less than or equal to y. So you get it as multiple region in this. So this is the portion where y is less than small y, right? And not this region. Again, this region is going to be what? Y less than small y. And here we have a region y less than what? Isn't it? The shaded portion is not important. What I am talking about is corresponding x. Whatever the curve, right? We have to look for the curve that crosses the straight line. And you have to find out the corresponding x. Isn't it? So you will have multiple region here. So the probability of y less than or equal to y is equal to what? So probability associated with this x region, probability of x associated with this region, and so on. It will end up with what? Multiple region. You understood this point? This point I just wanted to stress. Yesterday what we were discussing, right? So the single rectangular piece what we consider in the x1, x2 plane need not always end up with what? Single parallelogram in y1, y2 plane. That you have to be careful, right? So today we are going to discuss about how to generate the data with the required density function. That's what, this is just a recap what we had yesterday. So we'll start with generation of Gaussian density function. The technique is, we always start with the data that is of uniform distributed. Then we convert to the required density function. How that is possible, right? So if I have a data x, and this is my fx of x here, which is basically uniformly distributed between 0 to 1 like this, and you see the cumulative distribution follows like this, which is basically the integration of this, right? So you get like this 0 to 1 in this, and 0 to 1 here, and this is x, and this is going to be what? What? The distribution function. And you see that for the range that x between 0 to 1, the value of this distribution function is what? X itself, isn't it? So what is it, fx of x? Is x itself if x is ranging from where? 0 to 1, isn't it? And of course it is going to be 1 for x greater than 1. Are you getting this point? I am doing integration, right? Right, this value is going to be 1, 1 in this. If I do this integration, what is it you will get? Constant when you take integration, it is becoming what? X. Isn't it? So up to this, it is going to follow x, after that it is going to be constant. This property I am going to exploit. So if I have a random variable x which is of uniform distributed, then my distribution function is like this, that is equal to x for x ranging from 0 to 1, and then after that it is going to be that 1 always, right? Isn't it? So suppose that if I want to have, the random variable y, which is of some arbitrary distribution, fy of y, right? So what shall I do? I can generate the data which is of uniform distributed, and then I can find out the relationship y equal to g of x, which converts the random variable x to random variable y, which is of the required density function, right? So to start with, as usual, we start with this distribution function fy of y, which is probability of y less than or equal to what? Y here, right? And then probability of, I said that you find out that function that relating this y and x with some functional value g, y equal to what? G of x, right? So I replace here as g of x less than or equal to y in this. This is equal to probability of x less than or equal to what? G inverse of y, right? This is nothing but fx of g inverse of y here, right? The interesting point here is, we know that x is what? Uniform distributed. So we already know fx of x is simply what? X. If x is ranging from 0 to 1. It means that I can write this one simply g inverse of y, provided g inverse of y is ranging from 0 to 1. In fact, I wanted to get the result only for that range, 0 to 1. Are you getting this? This is for what? For g inverse of y is ranging from 0 to 1, because that is what we got it. Up to this it's clear? Are you getting this? What I am doing here is very simple. I want the outcome of the random variable y, which is of some arbitrary density function fy of y. So what you do? You start with the outcome of the random variable x, which is of uniform distributed, that is x. You got the raw data. In MATLAB, that is actually obtained using the command rand, R-A-N-D, right? You get a data now. Now what I do, I apply the transformation to this random variable x to get the another random variable y with the required density function. If I know this density function, I can find out the distribution function Fy of y, which is basically probability of y less than or equal to y here. Then I substitute y as g of x less than or equal to y here, and x less than or equal to g inverse of y here, and then what I'm writing in terms of distribution, fx of g inverse of y, right? But we know, this is what I told, I'm using this property, fx of x is equal to what? X. So this is becoming what? Simply g inverse of y. So what is my function now? We need a function g. Once you know the function g, you are through. Isn't it? You got the point? So what is my g now? Can anybody tell me that answer? What is g? I have in the left hand side as what? Fy of y. Your g inverse is same as that of what? Fy, the distribution function. As simple as it. So for example, yesterday we were discussing about this Rayleigh distribution. I hope this is right. This is the expression, and of course this is going to be 0 for r less than 0, that I am not writing. Right, this is the distribution function. I hope it is there in your notebook. Isn't it? We already know, if I have the outcome of the Rayleigh distribution, then I can get the outcome of what? Gaussian distribution. How? That I just recollect whatever we discussed yesterday. Right? So we have something like, x equal to r cos theta and y equal to what? R sin theta. Right? This R is Rayleigh distributed. And this theta is uniformly distributed between 0 to 2 pi. Right? And R is what? Rayleigh distributed. I repeat, if I have the outcome of Rayleigh distributed, that is R, and if I know the outcome of the uniform distributed theta, then r cos theta will give you what? The Gaussian distributed data. For every such values of r and theta, if I compute x cos theta, you get for every theta then r, right? You can choose randomly this theta and then what? R, and if I do this product, isn't it? So I get the output of what? The random variable x, I can collect it. If I say what is the nature of this distribution for this x, it is going to be what? Gaussian distributed. But now how to get Rayleigh? That is the question, right? Theta is fine. Theta is very simple because already it is uniform distributed. So I can comfortably use rand. That is basically coming from the PN sequence, right? So uniform distribution is known, and that is multiplied with what? 2 pi. So you get the values between what? 0 to 2 pi, which is of uniform distributed, done. But what is left out now is the Rayleigh distributed, isn't it? So that's what I am talking now, to how to get this Rayleigh distributed data, right? So for that what you need is the density function, which is known to us, and as far as this discussion is considered, we are trying to find out this g. To find out this g, we need this cumulative distribution function, right? So we quickly find out what is that cumulative distribution of this. So what is that? It is from 0 to r here, r by sigma square e power minus r squared by dr, right? So let me put r squared is u and 2r, dr is du This is the usual thing, and right. So 1 by sigma squared, I'll take it here. R dr is du by 2, so you get 2 here. E power minus u by 2 sigma squared here, right? So that is equal to, I'm not substituting limit, I want to rewrite finally the answer in terms of r. So this is becoming 1 by, so I'll bring this one to the numerator, so 2 sigma squared will come in this place with the negative sign, and that is equal to minus e power r squared by 2 sigma square. Now I apply the limit 0 to r here, so that is becoming what? 1 minus e power minus r squared by 2 sigma square. I hope this is right. Just check. What I have done is that just the integration. Strictly speaking, I should take integration from where? Minus infinity to r, some arbitrary value. But from minus infinity to 0, it is 0. So I have taken it from where? 0 to r. Isn't it? So I found that distribution function for the Rayleigh density function. This is a distribution function for the Rayleigh density function. Straight away I can, this is going to be my G inverse, right? G inverse. How to find out G? It is just that, what is that? Inverse of G inverse will give you what? G. It means that if I equate this one to some number, let us say that it is x, and if I solve for r, that will give you G, isn't it? So quickly we will find out that e power minus r squared by 2 sigma square, 1 minus, that is going to be your x, that's what I said here, right? So we'll take e power minus r squared by 2 sigma square that side, and this is going to be 1 by x, and take ln here, minus r squared by 2 sigma square, ln 1 minus x here, and then r squared is what? Minus 2 sigma square ln 1 minus x here, and then 2 sigma square ln 1 by 1 minus x you will take here, and that's going to be your r square here. So r is square root of 2 sigma square ln 1 by 1 minus x. I hope this is right. So don't just copy as it is, please work out. If you find out some right change, right, you please inform me, let me correct on the board. I'm just telling only the steps, right? So exact thing, you must not do any mistake, isn't it? So what the idea is, you have to start with finding out what? The distribution function. And my distribution function itself is my G inverse, that is the point, right? Fy of y is itself what? G inverse of y. So we need G. Finally what we need is G. How will you find out G? Very simple. G inverse of y, if I make it into x, y is becoming what? G of x. I get G now. That's what the trick I am doing. I am just equating to some constant and I am solving for it. If I find that, and this is the function now, it is of what? G. You got the function G now. So G of x. So in this expression, x is of what? Uniform distributed function, and R is Rayleigh distributed function. That's what I said. You start with uniform distributed data and get a Rayleigh distributed data, R, right? X is of uniform distributed data, which is of between 0 to 1, and then you get a data for what? The Rayleigh distributed.
The other density function we can also obtain by this method.
Yes, that's what I'm telling you. Any arbitrary density function you can have, not necessarily only for the Rayleigh. Any density function you can have it. The steps are very simple. What are the steps? You compute the cumulative distribution. and just equate to what? X, and solve for it, you get a function which converts the uniform distributed to arbitrary distribution. Here it is a Rayleigh distributed. I am explaining the Gaussian, that's the reason I am doing this job. Once you get this Rayleigh distributed data from uniform distributed, then I can get what? The Gaussian distributed data, which is of what? X equal to R cos theta. Remember that R is Rayleigh, theta is uniform distributed, which is between what? 0 to 2 pi. Is it clear? I just give you a few minutes to think recap what we are discussing. We are trying to generate the data with a specific density function, exponential or whatever you want, right? Here it is Rayleigh, chi-square. Whatever the density function you want, we need a data for doing the simulation. Right? In telecommunication we need it. We need to generate the Rayleigh noise. The noise with of what? Rayleigh distributed. We need to mimic or we need to what? Do that simulation on that. We need to generate it, the Rayleigh distribution. Right? So what exactly we have to do? We have to generate the uniform distribution. That is the starting point. And then you convert that uniform to the required density function. Right? For doing that, what you do, for example, in this case, what I have done? You compute the cumulative distribution of the Rayleigh density function and just equate this cumulative distribution function to some equal to X and solve for R, and that gives you G, Y equal to G of X. Right? Which converts from X to Y. In this case again X to R, isn't it? X is of what? Uniform distributed data, and R is going to be what? Rayleigh distributed. Once you know the Rayleigh distributed data, then we know theta, which is of what? Uniform distributed data. Then I can get Gaussian distributed data, which is X as well as what? Y. Both are Gaussian distribution. Right? And if I choose this variance to be 1, you get a Gaussian data with variance 1. Right? It means that the covariance matrix, let us consider this X and Y, they are Gaussian distributed, both are Gaussian distributed, right? Associated with what? Two random variables, X and Y, which is described by the covariance matrix and the mean vector. Mean vector, let us say mu X and mu Y, right? But the variance, based on what value you are choosing in this, right, you get that required variance. And yesterday we were discussing, what about that mean? Yesterday we were discussing the finally, right? What is that? If you are having this Rayleigh distributed data, and B, it will end up with what? Joint density function of what? Gaussian. You know that R equal to root of X square plus Y squared. Using that transformation, see the notes. R equal to what? Root of X squared plus Y squared. We used it, right? And finally we got a relationship, FR of R. In that case we got this Rayleigh relationship with the assumption that what? X and Y are Gaussian distributed with mean 0, variance sigma square. So exactly the reverse will happen now. Your random variable X and Y, they are going to be the Gaussian distributed data with mean 0, variance sigma square. But that alone is not enough. We already assumed that they are what? Independent, they are uncorrelated. In Gaussian there is a speciality. If it is independent, it is automatically uncorrelated. If it is uncorrelated, it is always independent. But it is not true for all. We already discussed that. Anyhow, we will discuss in the coming classes in detail. Right? So what do you say about this covariance matrix? So I just wanted to write this covariance matrix before we further discuss. So what is covariance matrix? So if I have a vector here, I form a vector with two random variables x and y, is a vector now, right? So the covariance matrix, let us say this Z bar is a vector now, right? So expectation of Z transpose minus mu Z transpose is the covariance matrix CZ. What is this? This is x and y in column wise, and this is row wise x and y. So what is the size of this? It is going to be 2 cross 2, right? In fact, if I find this, so what about this element? Very simple, you tell me what is that. You have here what? X and y, and here x and y. Column wise xy and row wise xy. What is the first element? It is x square. Second element is xy. And third element here, it is xy again. And this element, it is going to be y square. Right? The contribution from that first part is going to be your expectation of x square in this. And here you get what? Expectation of y square. Right? And here what is that you get? Expectation of xy. I am talking about only this first component. We have that second component also. Right? Mu Z. Mu Z is basically that what? Mean of x and mean of y arranged in what? The column form. Right? So you get here as what? Mu x, and this is what? Mu y, and this is what? This vector mu z. Isn't it? So when I compute this mu z transpose, what is the first element you get? What is it you get? Mu x square. Right? Here what is that you get? Minus mu x square. Here what is that you get? Mu y square. And here what is that you get? Mu x, mu y. And this one is mu x, mu y. This is what we call it as this covariance matrix. Expectation of Z transpose minus mu Z transpose is what we call it as the covariance matrix. Right? And this is giving the description about how far these two elements x and y are what? Correlated with each other. And if this value happens to be 0, we say that x and y are uncorrelated. Not independent. I am not saying it is independent, it is uncorrelated. Right? But for Gaussian, it is both ways are true. If I say independent, it is uncorrelated. If it is uncorrelated, it is independent. Only for Gaussian. In general, if you make this data as what? 0, it becomes what? X and Y are becoming what? Uncorrelated data. Why I am telling this one is, you are actually generated two Gaussian, X and Y, they are actually uncorrelated. That's what we had it, no? We proved yesterday. X and Y are uncorrelated. Isn't it? And of course the mean is 0. Now the requirement is to generate that Gaussian data with some arbitrary what? Covariance matrix, which is not going to be diagonal. This case it is becoming diagonal. This is becoming 0, and this is becoming 0, and this is the variance. And in fact for our case, if I choose the sigma square as 1, this is becoming what? 1 and this is also becoming 1. It is actually becoming the identity matrix. The covariance matrix of the data what you have generated, if I choose the sigma squared is equal to 1, it is going to be what? The identity matrix. Suppose if I want to have the Gaussian data, right, which is of having some arbitrary covariance matrix, right, again we need to go for what? A transformation of random variable. I repeat, what we have done now is we have already generated the Gaussian data x and y, but individually their mean is 0, right, and the variances are 1. Of course, if I choose the sigma squared to be 1 in that expression, it's a normal data what we have generated, x and y, they are what? Uncorrelated. Means if I compute this covariance matrix, it is ending up with what? The identity matrix. Suppose if I want to have another, right, random variable, right, 2 random variables, right, again needs to be Gaussian with some other mean and having some arbitrary covariance matrix. Arbitrary means something like this. You will be given this value, right, like this. So this is the arbitrary covariance matrix. If you are given some matrix, covariance matrix, I am asking you to generate the data. I need a data, right, which is described by 2 random variables, x and y in this case what I have chosen, right. We need some conversion, right. Make it as clear that I am going to now write this one as x1. I am not removing that, I just wanted to write this one as x1 or x2. This I am doing because I wanted to convert this x1, x2 into y1, y2. Change of random variable I am going to do now, right? Again, okay. So you are given a random vector x1, x2. I need to convert this one to what? y1, y2. They needs to be related. They are related now using what we call it as this transformation matrix. I write it here as y equal to ax plus b. A is some matrix. What is the size? This is 2 cross 1. This is 2 cross 1 here, and this is what? 2 cross 1, and this is becoming what? 2 cross 2. I need a transformation matrix A which converts the random vector x into what? Random vector y. And of course another vector is there as b here, constant. This matrix A and B are constant. They are linearly related. So can somebody tell me what is the expectation of y? I think you tell me that.
Expectation of x.
Huh?
A into expectation of x.
A into
Expectation of x.
x, that's all?
Plus b.
Plus
b.
b. Because a is constant, right? So I can bring the expectation operator inside. So expectation of x plus b is constant, expectation of b is going to be fixed, that is going to be b there as it is. So if I find out this expectation of y, it is going to be what? A into expectation of x plus b. Suppose that we already know that this expectation of x is what? What is expectation of x? In our case,
mu.
what is the value you got? What is the expectation of x? I mean, 0. Right? We already generated the data which is of having what? Expectation of x as what? 0. So this is 0 here, and we have only b. It means that expectation of y is becoming what? The b vector. It means I can choose any value for what? B, which helps me to shift the mean to the required one. Maybe the first data y1 can have the mean, right? Some value like b1, and this can have the mean as b2. If I want to do that conversion, I have to choose ax plus b. Interestingly, right, whatever the matrix you choose, it is not going to affect what? The mean, because mean of x is going to be what? 0. Whatever the value you choose for a, it is not going to affect, isn't it? But I already told not only the mean, we need the required covariance matrix, that is Cy. Right? So tell me what is Cy, how they are related. We got the relationship between this mean. How this covariance matrix of the vector y, random vector y, and the covariance matrix of the random vector x are related. I'll give 3 minutes time to find this answer. You know the definition for it, so you can tell me the answer. So what is that? Here you need to find out this. Actually, expectation of y transpose minus mu y transpose. This is what I am asking you to find out. Who is telling? And you substitute y as ax plus b. Right? Do it. I have given the time actually. Isn't it? So here expectation of this y is what? Let me do it here, but don't see, do by yourself. Ax plus b, the transpose, right? So what is this value? Minus, of course, we have this mu y. Mu y we already know what it is. A mu x, this is 0 in here for, but anyhow we'll make it as more general. A mu x plus b into plus b, the whole transpose. Still the second term is, right, is constant. The expectation operator is not going to play the role. The first one is important, right? You have 4 terms in this. Ax, x transpose, A transpose is there, right? Ax, B transpose is there. B into what? X transpose, A transpose is there, and then B transpose is there, and here again what? A mu x, and this is giving you what? Mu x transpose, A is there, and A mu x, B transpose is there, B mu x transpose, A transpose is there, and then finally B transpose is there, right? You cancel out whatever is possible and tell me what is that final result. I have given all the answers. It is only the algebra you have to do. Right? For instance, if I consider this Ax and this B, what is that you get? Expectation of Ax, B transpose, isn't it? A is constant, B transpose is constant, but X is a random vector. So what is that you get? A into mu X B transpose. You understood? I just give you only one for you to do further. So this is what I have taken, this part alone, AX B transpose, right? So in this case what I have to do? A is constant that I can take outside. Expectation of X is what? Mu X, and this B transpose will come as it is. But you will have the similar term in this. You see that A mu X B transpose is there with what? Negative sign. That will get cancelled. That's what I am asking you. Just expand it fully and cancel out whatever is possible and tell me what is the answer. So it is very important relationship what we have derived. Cy is equal to ACX A transpose. If I have a random vector y and x, they are related as what? Y equal to Ax plus B. Then my covariance matrix Cy is equal to what? ACX A transpose. Cy equal to ACX A transpose. It doesn't have B. The covariance matrix is not getting affected by this B, this vector B, right? It depends on only on the matrix A, right? Cy is becoming what? ACX A transpose. Why I am doing this? I am doing this because I just wanted to get conversion from where? X to Y. X we already generated, isn't it? X1 and X2 are what? Gaussian data with mean 0 and covariance matrix as what? Identity matrix, isn't it? And this Y we need to have some arbitrary covariance matrix. Is it clear? Right? So the problem what is given here is, you will be given this and you will be given this. The requirement is to generate the Gaussian data y1 and y2. They are having this mean as what? Mu1, I mean here it is given as b1 and, I'm sorry, this one you write as mu y. Okay? Mu y as what? b1 and b2. The mean vector is what? b1 and b2. Got it? And the covariance matrix is this. If you are given like that, straight away I can write b is equal to what? Mu y. That is very simple, right? I can simply equate this one as what? B vector. There is no problem in it. I can change the mean just like that, just by adding b. Fine. But to get the required covariance matrix Cy, I need what? A. If I know A, right, then I can what? Convert x to y such that my covariance matrix of what? Y is becoming like this. You got the point? So you will be given like this. This is not only for 2 cross 2. Whatever we derived is for 3 cross 3, 4 cross 4. Whatever the dimension you want, it is going to be true. Right? So, but what is the covariance matrix of X, which is having the two elements x1 and x2, which is identity matrix? Isn't it? Right? Now, to do this job, right, what we are going to adopt is the diagonalization. What is diagonalization? If I have matrix A that is said to be diagonalizable, I am telling you an important statement. If I have some matrix, arbitrary matrix A, and that is said to be diagonalizable, if I have another matrix called M, invertible matrix called M, such that M inverse AM is equal to D. Have you heard about this one earlier? You know that? Good. How many of you know diagonalization earlier? Good. So you are knowing that, right? Diagonalization, right? So what is diagonalization? If the matrix A is said to be diagonalizable, then there exists a matrix called M that should be invertible, right? And then what? M inverse AM, that is becoming D. D is the diagonal matrix. It is not actually all the matrices are what? Diagonalizable, not possible. But some group of matrices, some family, right, some property, having the matrices that have some property can be what? Diagonalizable. For example, the symmetric matrix is diagonalizable. Here this covariance matrix is the symmetric matrix. It is going to be what? The diagonalizable. We can diagonalize this Cy. It means that I can write this Cy, right? I can find out some matrix, right? M inverse Cy, M, that is becoming what? D. It is possible. In fact, we can actually find out that matrix M inverse in this case happens to be, you know, anybody? Orthogonal matrix, which we called as what? Eigenmatrix. Slowly I will tell you what I am trying to say here is, I have a matrix Cy in this. I can find out the matrix E, which is basically the eigenmatrix, means the eigenvectors of the matrix Cy, right? Suppose if the matrix Cy is of size 2 cross 2, how many eigenvectors you expect? You expect 2 eigenvectors in this case, and these 2 eigenvectors, you can find out they are going to be orthogonal. You can even make it as orthonormal. I hope you know what it is, right? Orthonormal means what? The magnitude is 1 and they are, when you take the dot product, it becomes what? 0. Right? And that is the reason, instead of writing it as inverse, I have taken simply what? The transpose. H is Hermitian transpose because, right, we can even have that element with what? Complex numbers. Transpose with what? Complex conjugate is what we call it as Hermitian transpose. So I am telling many points. If you already know, just have a note, otherwise you have to be seriously note. Right? So these things are very important, I am telling you. Right? So there are reasons why I am telling this one. Right? So you have this Cy can be what? Diagonalizable, right? So if I write this the other way around, Cy equal to what? EDEH is the other way around I am writing. Right? And then I can write it as what? E d power of EH, and again E d power of, and this is I here, d power of here. It's very interesting to say, I'm taking d power of. This is not possible for all the matrices. As the matrix is what? The diagonal matrix, this is possible. Just take the square root of the diagonal elements, provided they are all what? Positive. That's important. Fortunately, this is all positive because what is the diagonal elements? Diagonal elements are the variances, right? So all are positive. If I have a diagonal matrix, d power of is nothing but taking square root of what? The diagonal elements. Very simple. I am purposefully writing like this. Is there any reason?
To get A.
Huh?
To
To get A, good. I am trying to write in this way. Cy is what? E d power of I d power of EH. What is my A?
E d power of.
Huh? Yeah, tell me, you are right.
E d power of.
E d power of. You see that? Cy is what? A Cx, A transpose. Cx is your identity matrix. Right? So, what is my A? A is simply E d power of. That's it. So, what is the step? It's very simple. Now, I'll write the steps. Right? So, this is A equal to what? E d power of. That is the answer. Right? So what is the step? Let me summarize. What are the steps involved in getting multivariate Gaussian density function? I call it as multivariate, meaning you have more than one random variable in that. Right? You have two random variables in this, but it can be even be extended to 3, extended to 4 and so on. Right? Here it is what? 2 random variables. You can even do this job for 3 random variables, 4 random variables and so on. Right? So that's what we call it as multivariate Gaussian density function with arbitrary mean vector and arbitrary covariance matrix. So what you have to do, we have long process, right? So first step is to generate the uniform distributed data and get a Rayleigh distributed. That is one job. Again, generate a uniform distributed data, theta is ready. And remember that this normally you do this mistake. The data what you have generated for getting this Rayleigh, that is uniform distributed data. For getting theta also you need what? Uniform distributed data. You should not use In fact, you must not use the data what you have generated, right? The uniform distributed data, which actually you use it for what? R, for generating R, for theta. You should generate again. That's very important. If you use the same, you are purposefully making some correlation and it spoils. Right? So this is very important. What you have to do is, you have to generate the uniform distributed data, get R. Get uniform distributed data, get theta. And then get x1 and x2, which is what? x1 is R cos theta. x2 is R sin theta. You got this Gaussian data now, right? And while doing this generation, choose this sigma square is equal to 1. In this expression, I erased that, it is there in your notebook. During that conversion process, you choose the sigma square is equal to 1. I am choosing this one because I want the data, whatever you have generated, should have what? The mean is 0 vector and covariance matrix is the diagonal, identity. Job over. Then what you have to do is, you have to find out this eigen matrix, E. How to find out this eigen matrix, E? It is basically, you have to find out that the eigenvectors of what? The matrix Cy. What is it? How do you find out this eigenvector for the matrix Cy? Cy will be given to you, right? So what is the step? You find it Cy minus lambda I determinant equal to 0 and solve for lambdas, right? I just quickly tell you that, isn't it? Determinant of this one is equal to 0. Get the eigenvalues, right? And then what? Cy minus, let us say this one is lambda 1, lambda 2 here, lambda I, Vi 0. What does this mean? Cy minus lambda I is identity matrix, right? Into this Vi, and this Vi is what we call it as eigenvector. This eigenvector lies in where? Of course, we are going to have a formal discussion in linear algebra, but I just tell you that this Vi lies in where? The null space. It lies in the null space of the matrix Cy minus lambda I. Have you heard about this null space? Anybody? Null space, column space, right? Anyhow, we are going to discuss one in formal linear algebra portion. But now what I am telling is, the vector V is said to be, right, in the null space of the matrix A if it satisfies the condition AV equal to 0. Now you understand that alone, and we will discuss that one later on. What is that? We have 4 fundamental subspace, right? So we will discuss that one later on. Now as of now you understand that the vector V is said to be in the null space of the matrix A if it satisfies what? AV equal to 0. So this vector Vi is in the null space of what? Cy minus lambda I. And you get 2 vectors here, V1 and V2. They are all the eigenvectors. And you arrange these vectors in what? Column wise to get a matrix E. Right? And that is what this matrix E. You arrange them in column wise, V1, V2, and that is a matrix E. That's what we call it as eigenmatrix. Right? And that is what you are getting it as. This A is what? E d power of. So what about D? the diagonal elements of the matrix D, they are all the eigenvalues of the matrix Cy, and you get this value, this lambda 1 and lambda 2, and that is going to be there in the diagonal elements, right? So D is a diagonal matrix with lambda 1 and lambda 2. So you can take what? The square root of lambda 1, square root of lambda 2, and they are going to be positive. They are going to be positive is very important information, because we already know that the diagonal elements of covariance matrices are what? The variances that necessarily needs to be what? Positive. 0 is okay, but 0 hardly you can have it, right? 0.001, something like that. But negative will not normally have, we cannot have variances to be the negative value. It's about the squared value, right? Sigma x1 square, sigma x2 square, sigma y1 square, sigma y2 square, like that. So they are all positive. So square root of lambda 1, square root of lambda 2. That you substitute here for D. And E is a matrix in which each columns are the vectors V1 and V2. Right? So once you know this A, then it is very straightforward conversion. What is that? Y equal to AX plus B. X is known, which we already generated. B is B1, B2. A just now we found. Use that. We get a outcome of the random vector Y, which is of what? Gaussian, multivariate Gaussian, right? Data distribution function, right? With the required mean vector and the covariance matrix, right? We'll quickly do one more task, right? See, I told that in this process of conversion, the main trick is you start with uniform distributed data, right? And then what? You get a required density function. That's what I said, right? You find out the distribution function equal to X and solve for it, and you get what? The required density function I told already. So you start with what? Uniform distributed data. Sometimes you need the reverse way. This is very helpful. One of the application I can tell you that it is histogram equalization in image processing. You already studied, no? How many of you heard about histogram equalization? Image processing? You studied image processing as the elective, right? Have you heard about histogram equalization? So what does it do?
Actually, we will normalize the grayscale values like on a plane, like from 0 to 255. Based on the in CDF we will do this. Combine density function.
Yeah. So basically, what we do here is the histogram of the histogram equalized data, that should be what? Flat, ideally. Histogram is nothing but density function in case of continuous, that is, there it is what? The mass function. It's a probability basically. It's in discrete form. Whatever we are discussing are all in what? The continuous. The same thing I can even try for the discrete case. Right? I wanted to do that also. It's very simple. I just wanted to make you understand that what is that histogram equalization. Right? So see, in case of image, if I consider this image, right? And you can see this type of tools in Photoshop, right? Isn't it? So where we have a menu bar there, we can choose this histogram equalization. If you click, an image looks better, right? Isn't it? So that is what I am talking about. So you have these gray values, right? 2, 3, 4 and so on. You have this 255, right? Like this. And you have the histogram for this. 0, 1, 2, 3 it goes like this to 55, and we can count simply these values here and divided by 255, that gives you that probability. This is the probability basically. It's a random variable x in this, and this is going to be our probability of x. You have some distribution, but after doing some conversion, I wanted this probability to be what? Equal, right? So it should be like this, ideally speaking. Ideally what I am expecting is this. Everywhere it is what? So what is this value, typical value of this? 1 by 256, right? Because you have 256 values, isn't it? So of course we can normalize it. I mean, you can say that it is 0 and this corresponds to 1. Instead of saying 0 to 255, I can divide everything with 255 and I can say that values of x are changing from where? 0 to 1, and you have the corresponding probability. After conversion from x to y, my probability of y is going to be what? Flat. Just basically in continuous case, what does it mean? I have some arbitrary density function, right? Something like this, and this is going to be my flat here, uniform distributed. And that is what exactly this histogram equalization is doing. It is exactly the reverse operation. You are given some arbitrary density function and you would like to have what? Uniform distributed data, right? So how do you do that? So we need again a conversion, right? Y equal to g of x, right? So we need this function g, but we know the property only for the uniform distribution. What is that? Probability of y less than or equal to y is what? Cumulative distribution. We know that is the basic, right? That's where we started. Fx of x is becoming simply what? X. So here it is y. Y is uniform distributed, right? X is arbitrary and y is uniform distributed. So Fy of y is y. And that is what we are going to do, right? So I am simply writing this Fy of y is what? Probability of y less than or equal to y in this, and that is equal to probability of g of x less than or equal to y in this, and probability of x less than or equal to g inverse of y here, and this is fx of g inverse of y here, and this is my Fy of y, and I told you that Fy of y is simply y, and remember that this y is should range from where? 0 to 1. That is very important. Even though I am not writing, but you know the characteristics of what? Fy of y. That is going to be y only when what? Y is ranging from 0 to 1. And you remember that this x and y, they are now having that values from 0 to 1 only. That can be done simply. See, what you do is, it is only the representation, right? Pixel, gray values. Instead of saying it is a 255, you call it as what? 1. Instead of saying it is 1, you call it as 1 by 255. You understood what I am telling? Right? Is it clear? You can simply rewrite this. If you are not comfortable in saying this statement, you make it as conform everywhere divided by this, and it is going to be your 1 in this. I am doing this because my values for x and y, they are going to have the range from where? 0 to 1. That is what I wanted to what? Confirm. right? So it's very simple now. So fx of g inverse of y is y. Then what is my g? Fx of g inverse of y is y itself. Then what is my g? Huh? G is fx inverse. Is that g fx inverse? Huh? G is fx. That is right. Because we want to negate them. We are doing some function. Again I am doing a inverse function. Then only I will get y. Combined together it should be simply what? Cancel each other. Is that right? So my g is as simple as that. It is nothing but your cumulative distribution, fx of x. Isn't it? So if you are given some density function like this, I mean, in case of discrete it is going to be your mass function like this, I can find out what? The distribution function. Cumulative distribution function. Isn't it? Then the conversion is the cumulative distribution function itself is the answer for me. What does it mean? How do you write the code for it? Or in image processing, what is that you do in this? What exactly you have to do for histogram equalization? You got this values, right? And then you have to go for what? Cumulative distribution function, fx of x, right? And just so let me put it as a here, or b here, or c here. Some number will be there, right? So this is 0. Right? Very simple now. What does it mean? If you are given an image, if I see the pixel with number 2, for example, this case, then I have to go for this, then I have to see what value it is. This is what? C, right? And that C you have to multiply with what? 255, and you want that gray value to be the integer. So what do? You take round it. Basically, not absolute means what I really mean by that is rounding, right? Fix or round to make it as what? The integer, and that value you put it here. Instead of 2, you substitute that, isn't it? Are you getting this point? Every pixel value in that original image, you have this function. How this function is coming? Is simply the cumulative distribution. Because my g is same as it of what? Fx of x. If I do this process, I get that image looks what? Better. If I have an image taken from the satellite, you don't know the reason why this image is getting what? Distorted. Somehow I wanted this image to look better. Right? We try with different tools in Photoshop, right? And we have a tool called what? Histogram Equalization. Just like any other tools, right? So if I click that, you get that image to look better. The reason is it is boosting up, right, the pixels which is actually occurring very less number of times, that also to more number, and at the same time whatever is available large, that is coming down. You are balancing that, right? So whatever is dark in that image, that gets boosted up. You get a better visual of the image, and that's what we call it as histogram equalization, right? Let me stop today's class with that final question for you. You can think and you can tell me the answer for that. Suppose that I have a image, right, and I am seeing another image which looks really good. I wanted this image to look like that. It doesn't mean that the content is changing. Content remains the same, but the visual, the brightness in that, whatever you feel on seeing one particular image, which looks good. This is taken here, so you have another image which is not that much good as that of what you are having, right? I want this image to look like that. Means mathematically what I am trying to say here is, I want the distribution, the probability mass function of the given image, right, to look like the probability mass function of the reference image. You see, even here, if I do this conversion, if I plot this histogram, don't expect that it is perfectly flat. No, you will not get. Unless it is continuous, you will not. Actually, what we have derived at all is what the continuous. It's for the density function. This is just the approximation of the density, right? I mean, here we are using only what? The mass function, and here we are trying to make it as uniform. And this, if I find out these values, they are not strictly equal, but compared to that P of X, and if I plot this P of Y, that is going to be almost equal, right? So now I have given a problem for you, right? So you have 3 random variables now. I just give you only the hint. You try and tell me that answer, right? We have 3 random variables. X is the image what you have, right? Z is, you have seen some image, and that is Z. I want this X to look like Z. Means the mass function of X, right? I want to convert them to the mass function of what? Z. To do so, I am introducing a new random variable called Y, which is in the middle, which does the job of what? X to Z. How? That's what I am telling. X to Y, first of all. Y is of uniform distributed. I'm just giving you the hint. And we have Z here. That also you can convert into what? Uniform distributed. Then you have a mapping, isn't it? We know 2 things. How to convert from arbitrary to uniform, uniform to arbitrary, job over. If I have these 2 information separately available, right? X to Y means arbitrary to uniform. And then what? Y to Z, uniform to some other arbitrary. If I know these 2 conversions, then I can do what? Histogram specification. You understood this point, right? So I want you to think about this, right? And you can write the steps involved, just like whatever I told for histogram equalization. You can write the steps for histogram specification. Means you are given some reference histogram, you are given the image whose histogram, right, should look like that. That's the meaning of it, right? That's called, you have a reference image. I want this image to look like that. Looks like the same brightness, contrast, everything, right? So what are the steps involved in this thing? Okay, we'll stop here. Okay, so who is taking? Who is taking the alternance? Last time, yeah. So just note down. What you can do is, when the class starts, you just circle it. You circulate it. No, at the beginning of the class, you can simply circle it.